At 2:17 a.m. on February 3, 1943, Foreman Carl Dietrich slid a feeler gauge into the gap between turret number 4847 and hull number 4847 at the Detroit Tank Arsenal in Warren, Michigan. The smell of cutting oil hung thick in the air. Pneumatic hammers echoed from 3 bays over. Yellow overhead lights cast sharp shadows across the assembly floor. 4 workers had been fighting this turret for 9 hours. They'd lowered it onto the hull ring at 5:30 p.m. the previous evening. Since then, they'd filed, shimmed, adjusted, measured, adjusted again. The turret was suspended by an overhead crane, swaying slightly. The hull sat on wooden blocks. Dietrich checked the north side first. The gauge slipped in easily. 0.09, 5 inches of gap. Too much. He moved to the south side. The gauge barely fit. 0.003 inches. Too tight. He pulled a red rejection tag from his pocket, wrote the turret number, hung it from the crane hook. "Send it back," he said. The 4 workers said nothing. They'd known for the past 3 hours this turret wouldn't work. They'd kept trying anyway because sending a turret back to the foundry meant paperwork, explanations, and 340 man-hours wasted. This was the 3rd turret rejected that night. 50 yards away, in the tool crib's small office, Margaret Nowak watched through the window. She'd been watching turret installations for 3 weeks. She'd seen this same scene 47 times, and she knew why it kept happening. The Detroit Tank Arsenal had a catastrophic production problem. Target, 12 Sherman M4 medium tanks per day. Actual, 8.3 tanks per day. The bottleneck was turret installation. Average time, 11.2 hours per unit. The process was brutal. Overhead crane lifted the 5-ton turret. Workers lowered it onto the hull ring. Then the fitting began. Hand files to shave down high spots, hammers to tap components into alignment, shims thin metal strips wedged into gaps, grinding wheels to smooth rough edges. Workers used levels to check horizontal, plumb bobs to check vertical, feeler gauges to measure gaps. They eyeballed alignment because no precision measuring tools existed for something this large. Test the turret rotation. Binding on the left side. Adjust. Test again. Binding on the right. Adjust. Test. Still not smooth. Start over. Minimum time, 8 hours. Maximum, 16 hours. Sometimes the turret never fit properly at all. Out of every 100 turrets manufactured, 23 got rejected. 23 turrets sent back to the foundry, melted down, recast. Each rejection cost 340 man-hours. Each rejection added 6 days to the delivery schedule. In January 1943 alone, Detroit Tank Arsenal scrapped 89 turrets. That was 89 tanks the Army didn't get. 89 5-man crews training without their assigned vehicles. 89 holes in armoured battalions deploying to North Africa. An Army Ordnance memo from January 28 stated it clearly. Every tank not delivered is 5 men driving into combat in a vehicle we didn't provide. The engineering solution was to tighten in manufacturing tolerances across the entire supply chain. But the turrets came from 3 different foundries in Michigan and Ohio. The hulls came from 2 separate assembly plants. Coordinating tolerance improvements across 5 facilities would require new tooling, new inspection procedures, new quality control systems. Timeline, 8 to 12 months. The Army's response came back in 3 days. "We don't have 8 months. We need tanks now." But the Arsenal didn't have a solution. The engineers were still calculating tolerance stacks. The production managers were still filing reports. And every night, crews kept fighting turrets that wouldn't fit. Margaret Nowak was 34 years old, jig builder, tool and die department. Before the war, she'd worked in her father's machine shop in Hamtramck, building custom fixtures for automotive assembly lines. She'd been solving alignment problems for 16 years. She arrived at work 30 minutes early every day, kept a notebook of production inefficiencies, had Already designed 7 minor jigs that improved workflow, a fixture for aligning final drive housings, a cradle for stabilizing gun mount assemblies, a positioning tool for periscope installation. The floor workers respected her, management tolerated her. She was good at her job, but she was a woman in a man's industry, and that put a ceiling on how seriously anyone took her ideas. Over the past 3 weeks, she'd watched 47 turret installations. She stood in the tool crib office window and tracked every adjustment, every measurement, every failure point. She wrote down the numbers, calculated the averages, identified the pattern, and she realized something the engineers hadn't. The parts weren't the problem, the process was. Both turrets and hulls were within specification. The foundries and assembly plants were doing their jobs correctly, but within spec meant variation. A turret ring might be 69.85 inches in diameter. Specification allowed anything from 69.825 to 69.875. A hull ring might be 69.87 inches, also within spec, but now you had a 0.02-inch mismatch, and the turret wouldn't sit properly. The current method tried to force variable part A onto variable part B. Workers compensated for the variation manually, using skill and experience and time, lots of time. NOAC saw a different approach. What if you constrained both parts in fixed 3-dimensional space first? What if you built a jig, a massive fixture, that pre-positioned both the turret and hull in exact spatial relationship to each other? The jig would locate both components against known reference points. It would compensate for manufacturing variation automatically. Then you'd bring them together under controlled force. The parts would mate correctly because the jig forced correct alignment. On February 3rd, watching turret number 4847 get rejected, she did the math in her head. Average installation time, 11.2 hours. Her estimated time with a proper jig, 4 hours. Savings, 7.2 hours per tank. The arsenal built 12 tanks per day. That was 86.4 hours saved daily. Over a year, 31,536 hours. At $2.40 per hour labor cost, $75,686 in annual savings. Whatever the jig cost to build, it would pay for itself. She made her decision that night. She'd build it herself, wouldn't ask permission, would prove it worked with a scale model first. Then they'd have to listen February 4th, 10:30 p.m. The day shift ended at 10. Most workers clocked out, headed to the parking lot, drove home through the Detroit winter night. Margaret Nowak stayed. The tool crib was empty except for her. She rolled out a 6-foot section of butcher paper across the main workbench. Brown paper, normally used for wrapping parts. She grabbed a pencil, a steel ruler, and a cup of coffee that had gone cold 3 hours earlier. She started with the fundamental problem. How do you hold a 5-ton turret and a 12-ton hull in exact spatial relationship to each other? The structure would need to be tall, 20 feet minimum, to provide clearance for the overhead crane. It would need to be strong, supporting 17 tons of combined weight plus dynamic loads during installation. And it would need to be adjustable because every turret and every hull would be slightly different. She sketched the basic framework, 4 vertical I-beams forming the corners, horizontal cross-members connecting them at 6-foot intervals, a lower cradle to hold the hull, an upper cradle suspended from the top to hold the turret. Both cradles adjustable. But the key innovation wasn't the structure, it was the locating system. She drew a series of small circles on her sketch. Spring-loaded pins, 24 of them. 12 would contact specific datum surfaces on the hull machined bolt holes, reference edges, flat surfaces. 12 would contact datum surfaces on the turret. The pins would be spring-loaded, able to travel 2 inches inward when they contacted their reference surfaces. The spring pressure would push them firmly against those surfaces. Here was the brilliance. The pins would automatically find the reference points regardless of where the part sat in the cradle. If a hull was sitting 0.03 inches too far north, the locating pins would compress more on one side and extend more on the other, but they'd still contact the correct surfaces. The jig would self-compensate for variation. Once both components were located by their pins, hydraulic rams would provide the mating force. 4 rams positioned at cardinal directions north, south, east, west, each capable of 5,000 pounds of force, controlled independently so you could apply more pressure on one side if needed. She worked through the load calculations. The turret cradle had to support 5 tons, 10,000 pounds. Add a safety factor of 3, 30,000 pounds. That required 12-inch I-beams, 40 pounds per linear foot. She calculated the hydraulic ram sizing. 4 rams at 5,000 pounds each gave her 20,000 pounds of total available force. More than enough to seat a turret that was fighting by a few thousandths of an inch. At 1:45 a.m., she had her breakthrough moment. It just needed to be more consistent than humans. Humans varied their approach every single time. Every crew lifted the turret differently, positioned it slightly differently, applied force from different angles. No 2 installations were identical, but a jig, even with its own manufacturing tolerances, would repeat the exact same sequence every time. Same locating points, same forces, same alignment. Consistency beat perfection. She kept working. February 5th, 10:30 p.m. Night 2. NOAC refined the design. Added manual adjustment wheels, large hand wheels connected to screw jacks for fine-tuning alignment. The locating pins would get you close, within 0.05 inches. The adjustment wheels would get you perfect. She planned the installation sequence. Hull enters the lower cradle first. Gets positioned roughly by the crane. Operator. Locating pins extend, find their datum surfaces, lock the hull in precise position. Turret lifts into the upper cradle. Its locating pins engage. Now both components are constrained in known positions relative to each other. Lower both cradles simultaneously. The turret ring approaches the hull ring. At 2 inches of separation, stop. Check alignment visually. Make fine adjustments with the hand wheels if needed. Then activate hydraulic rams. Apply even pressure from all 4 directions. Turret seats onto hull in controlled fashion. She drafted detailed drawings, 11 sheets, every dimension specified, every bolt size called out, every weld location marked. Her drafting wasn't as clean as an engineer's, but it was clear. Anyone could build from these drawings. She calculated material costs. 8 I-beams at 12 feet, each $2,400. Cross members and bracing, $1,800. Hydraulic components, pump, rams, hoses, valves, controls, $6,200. Spring pins custom fabrication required, $1,400. Structural plate for cradles, $1,600. Hardware, welding supplies, miscellaneous, $800. Total, $14,200. Labor estimate, 2 experienced welders, 160 hours total. At $1.85 per hour, $296. Round up to $300. Grand total, $14,500. Well under her mental budget of $20,000. February 6, 10:30 p.m., night 3. Time to prove it worked. NOAC gathered scrap materials from the tool crib storage area. Steel bar stock, 1, 8-inch thick. Threaded rod. Compression springs from a salvaged engine valve assembly. Small machine screws. She built a scale model. 1/10 size. The real jig would be 20 feet tall. Her model was 24 inches tall. She used wooden blocks to represent the turret and hull. Cut them on the bandsaw to roughly the right proportions. Deliberately made them slightly different sizes to simulate manufacturing variation. The model took 4 hours to build. She worked with hand tools, hacksaw, files, drill press, tap and die set. Her hands were black with cutting oil. Her fingers ached. At 2:40 a.m., she tested it. First test. She placed the hull block in the lower cradle offset to the north by 1/4 inch. The locating pin's actual small compression springs in her model extended and contacted the reference surfaces she'd marked on the block. The springs compressed more on the south side, extended more on the north side. The block was now located in correct position relative to the jig frame. She placed the turret block in the upper cradle, also deliberately misaligned. Same result. The pins located it correctly. She lowered the upper cradle. The two blocks came together. Perfect alignment. She tested it 14 more times, varied the starting position of both blocks. Different offsets, different angles. Every single time, the locating pins forced correct alignment. The blocks mated perfectly every time. She knew it would work at full scale. Now she needed someone with authority to believe her. February 7th, 7:15 a.m. Carrying her scale model in a wooden crate. She'd slept 3 hours. Her eyes felt like sand. Her back hurt from hunching over the workbench for 3 consecutive nights. But she had her proof. She found her supervisor, Thomas Brennan, in the production office. He was reviewing reject tags from the night shift. 4 turrets sent back. Another bad night. "I need 10 minutes," Nowak said. Brennan looked up. "I'm busy. I can fix the turret problem. Engineering is working on it. Engineering wants 8 months. I can give you results in 2 weeks. Brennan set down his clipboard. 10 minutes. Nowak lifted her scale model onto his desk. It looked absurd, a miniature industrial structure made from scrap metal, sitting between Brennan's coffee cup and his stack of production reports. "This is a jig for turret installation," she said. "Full-scale version will be 20 feet tall. Lower cradle holds the hull, upper cradle holds the turret. These pins," she pointed to the small springs, "locate both components in precise spatial relationship." She grabbed the wooden hull block, deliberately placed it crooked in the lower cradle. The springs engaged, pushed it into alignment. "See? The part can start anywhere. The pins find the reference surfaces automatically. Now watch." She placed the turret block in the upper cradle, also misaligned. Same result. The pins located it correctly. Now both parts are in known positions relative to each other. She lowered the upper cradle. The blocks came together perfectly. The jig forces correct alignment every single time. She did it again. Started with extreme misalignment. Same result. She did it a 3rd time. Perfect alignment. Brennan watched without speaking. "How much?" he finally asked. $18,000, materials and labor. "To save what? 4 hours per tank?" Nowak pulled her notebook from her coat pocket, opened to a page covered in calculations. 4 hours per tank times 12 tanks per day, times 365 days equals 17,520 hours saved annually. At $2.40 per hour, that's $42,048 in labor cost savings. Payback period, 5 months. And if it doesn't work? Then you're out $18,000. But you're already losing $75,000 a year in wasted labor. Plus the cost of scrapped turrets, plus the cost of delayed deliveries, plus the cost of sending tanks to combat that aren't properly aligned and break down in the field. What's the real risk? Brennan stared at the scale model, reached out and picked up the hull block, placed it deliberately crooked, watched the springs push it into position. "Come with me," he said. They walked to the plant manager's office. Richard Morrison was on the phone with Army Ordnance, explaining why last week's production numbers were below target. He saw Brennan at the door with a woman carrying a strange metal contraption and held up one finger. "Wait." Morrison finished his call. "What?" "Show him," Brennan said. Nowak demonstrated the model. Morrison watched the first sequence without expression. "Again," he said. She ran it 3 more times. Morrison picked up his phone. Dialed the Army Ordnance Liaison Office. "Parker?" "Morrison, I've got something you need to see." "No, now." Colonel James Parker arrived 20 minutes later. Watched the demonstration. Asked Nowak 6 questions about load capacity, installation time, and failure modes. She answered all 6 without hesitation. Parker looked at Morrison. Build it. Morrison looked at Nowak. You have 2 weeks and a $20,000 budget. If this works, you're a hero. If it doesn't, you're fired. Nowak nodded. Fair enough. When can you start? Today. February 8th, 6 a.m. Morrison assigned Nowak 2 welders, Pete Kowalski and James Turner. Both men had 20-plus years of structural welding experience. Both had built automotive assembly and fixtures before the war. Neither had ever taken orders from a woman. Morrison gave them Bay 12 on the assembly floor, 30 feet by 30 feet of empty concrete, currently unused because the overhead crane in that section needed repairs. The crane would be fixed by tomorrow. Perfect timing. You report to Nowak, Morrison told the welders. She designed it. She's in charge. Questions? Kowalski and Turner looked at each other. Neither spoke. Good. Get started. Nowak spread her 11 blueprint sheets across a work table they'd dragged into Bay 12. We start with the foundation, she said. 4 vertical columns, 12 feet high, positioned at these coordinates. She pointed to the dimensions on the drawings. She pulled a piece of chalk from her pocket and walked to the floor, marked the 4 corner positions, 12 feet apart north-south, 10 feet apart east-west. Each mark indicated where an I-beam would be anchored. The steel arrived at 2 p.m. Flatbed truck backed up to the loading dock. 8 I-beams, each 12 feet long, each weighing 480 pounds. Cross members, angle iron, steel plate, hydraulic components in wooden crates. Everything Nowak had specified on her purchase orders. Kowalski and Turner used the repaired overhead crane to move the first vertical beam into position, lowered it onto Nowak's chalk mark. She checked it with a level, perfectly plumb. Drill anchor holes, she said. 4 bolts per column, 2-inch diameter, 18 inches deep into the concrete. Turner looked at her. 2-inch bolts? That's overkill. This structure will support 17 tons of dynamic load. 2-inch bolts. He drilled the holes. They installed the first column by 5 p.m. 4 2-inch bolts anchored it to the floor. The I-beam stood vertical, rock solid. 3 more columns to go. February 9th through February 11th, 3 days of framework construction. The 4 vertical columns went up first. Once anchored, Kowalski and Turner welded horizontal, cross members connecting them. First level at 6 feet. Second level at 12 feet. Third level at 18 feet. Each weld inspected by Nowak. She checked every joint with a square. Checked every dimension with a tape measure. If something was off by more than 1/16 inch, they cut it and did it again. Turner questioned her twice. That's close enough, he said when a cross member was 1/8 inch out of position. Close enough means it fails, Nowak replied. Cut it, redo it. He cut it. He didn't question her again. By end of day February 11th, the basic skeleton stood complete, 20 feet tall, framework of I-beams and cross members. It looked like an industrial jungle gym. Workers from other bays walked over during breaks to stare at it. One foreman called it Nowak's circus tent. Another called it the world's most expensive coat rack. The welders said nothing. They were starting to understand what she'd designed. The structure was overbuilt deliberately. Every connection reinforced. Every load path calculated. This wasn't experimental. This was engineered. February 12th through February 14th. Cradle fabrication and locating system. The lower cradle came first. Steel plate, 1/2 inch thick, bent into a U-shaped channel 8 feet long. Mounted on adjustable supports so it could move up and down via chain hoist. The hull would rest in this cradle during installation. The upper cradle was more complex, suspended from the overhead beam at 18 feet, also U-shaped but smaller, sized for the turret base. This cradle could raise and lower independently via its own chain hoist. Nowak fabricated the spring-loaded locating pins herself. Each pin was a steel rod, 3/4 inch diameter, 8 inches long. One end was pointed to help it find its datum surface. The other end pressed against a compression spring. The springs came from a supplier in Detroit custom order, 200 pounds of spring force each, 2 inches of travel. She installed 12 pins in the lower cradle. Each pin positioned to contact a specific datum surface on the hull, a mounting hole, a machined edge, a flat reference surface. When the hull settled into the cradle, these pins would extend inward, find their surfaces, and lock the hull in precise position. She installed 12 more pins in the upper cradle for the turret. Each pin took 40 minutes to install. Drill the mounting hole through the cradle wall, install the pin assembly, install the spring, install the retaining hardware, check the travel. Check the spring force with a scale. Adjust if needed. 24 pins times 40 minutes equals 16 hours. NOAC worked through 2 full nights to finish them. February 15th through February 16th. Hydraulic system installation. The hydraulic pump arrived in a crate marked U.S. Army Ordnance Priority. Electric motor driven, 3,000 pounds per square inches capacity. Kowalski mounted it on a steel frame at ground level, 15 feet from the jig structure. They routed hydraulic lines from the pump to 4 rams. The rams were positioned at cardinal directions around the lower cradle: north, south, east, west. Each ram could extend 24 inches and apply 5,000 pounds of force. Turner did the hydraulic plumbing, steel-braided hoses, compression fittings, shut-off valves. He'd done hydraulic work before. He was good at it. He worked methodically, tested every connection for leaks, double-checked every fitting. The control station went in next to the pump. 4 manual valves, 1 per ram, 4 pressure gauges, 1 master shut-off, 1 emergency stop button. All controls within reach of a single operator. They tested the hydraulic system without load. Pump on. Extend ram 1. Check pressure gauge. 500 pounds per square inches, 1,000 pounds per square inches, 1,000, 500 pounds per square inches. Retract ram 1. Repeat for rams 2, 3, and 4. All systems nominal. February 17th through February 18th. Control systems and safety equipment. NOAC installed 4 manual adjustment wheels. Large hand wheels, 18 inches in diameter, connected to screw jacks. 2 wheels controlled the lower cradle's position north-south and east-west. 2 wheels controlled the upper cradle's position. Each wheel was marked with graduation lines. 1 full rotation moved the cradle 0.1 inches. The graduations were marked every tenth of a rotation, 0.01 inches per mark. Fine adjustment capability. Safety equipment. Yellow paint on all moving components. Grey paint on static structure. Barriers around the perimeter. Warning signs. Danger. Moving machinery. Authorized personnel only. Emergency stop buttons at 3 locations. She created the operating procedure. Typed it on Morrison's secretary's typewriter. 12 steps. Laminated the sheet with clear acetate and mounted it on a metal plate bolted to the control station. She trained Kowalski and Turner on the procedure. Walked them through each step twice. No turret or hull involved yet, just dry runs. Move the cradles, activate the pins without load, operate the hydraulic controls. Get familiar with the sequence. Both men learned quickly. February 19th, 4:30 p.m. Morrison arrived at Bay 12 with 3 engineers and the Army liaison. They'd come to see the completed jig. It stood 20 feet tall. Framework of I-beams painted grey, moving components painted yellow, hydraulic lines running from ground-level pump to elevated rams. 2 cradles suspended at different heights. Control station with valves and gauges and emergency stops. Warning signs. Barriers. It looked professional. It looked engineered. It looked like something that might actually work. Jesus Christ, one of the engineers said. She actually built it. Morrison turned to NOAC. Ready to test it? Yes. When? Tomorrow morning, 6 a.m. I need a hull and turret from the production queue. You'll get them. Morrison looked at the jig for another 30 seconds. If this works, Margaret, you're going to change how we build tanks. If it works, Nowak said, you'll be able to deliver 12 tanks per day like you promised. February 20th, 5:45 a. Nowak arrived at bay 12-15 minutes early. The jig stood waiting. She'd checked every system the previous evening before going home. Hydraulic pressure, good. Locating pins, all moving freely. Chain hoists, operating smoothly. Control valves, no leaks. But testing with empty cradles was different from testing with 17 tons of steel. Morrison arrived at 5:55 with a crowd. 8 engineers, 4 foremen. The Army liaison, Colonel Parker. 12 workers from the night shift who'd delayed going home to watch. Everyone wanted to see if Nowak's circus tent would work or collapse. At 6 a.m. the overhead crane brought hull number 5104 into Bay 12. Morrison had deliberately selected this hull. It had been flagged by quality control as marginal, barely within specification. The turret ring diameter measured 69.873 inches. Maximum allowed, 69.875 inches. This hull represented the worst-case scenario. The crane operator, a man named Vincent, who'd worked at the arsenal since 1941, lowered the hull toward the lower cradle. Slowly. The hull weighed 12 tons. If it dropped too fast, it could damage the cradle or bend the frame. Nowak stood at the control station. Easy, she called. Another foot. 6 inches. Stop. The hull settled into the U-shaped cradle. It wasn't centered. The north side sat about 3 inches higher than the south side. Deliberate positioning by Vincent to test the jig's self-correction capability. Activate locating pins, Nowak said. Kowalski threw the pin control lever. Compressed air hissed through lines. The 12 spring-loaded pins extended inward from the cradle walls. 11 pins found their datum surfaces immediately. The 12th pin mounted on the northeast corner struggled. The reference mounting hole it was searching for was 0.04 inches off nominal position, out of spec but not unusual for a marginal hull. The pin kept extending. The spring compressed. Finally, the pointed tip found the hole edge and slipped into position. All 12 pins engaged, Turner called out. He was walking around the cradle, visually checking each pin. Nowak checked her position indicators dial gauges mounted on the cradle frame. They showed the hull's position relative to the jig's reference frame, north-south, centered within 0.015 inches. East-west, offset 0.022 inches to the west. Close enough. The hydraulic rams would correct that during final mating. Bring in the turret, Nowak said. At 6:09 a.m., the crane brought turret number 5104 into position. This turret had also been flagged. The turret ring measured 69.827 inches, minimum allowed was 69.825 inches. Combined with the oversized hull ring, this pairing represented the worst possible combination of tolerances. Under the old method, this turret and hull would take 14 to 16 hours of fitting, probably get rejected, maybe both components sent back for rework. Vincent lifted the turret into the upper cradle. It settled with a metallic thump, also deliberately off-center. Activate upper pins, Nowak said. Kowalski threw the second control lever. The upper 12 pins extended. 10 pins engaged immediately. 2 pins hesitated. One found a machined surface that was 0.035 inches low. The other found a reference edge that was slightly rounded instead of sharp. Both pins adjusted, compressed their springs, and seated properly. All upper pins engaged, Turner confirmed. The crowd pressed closer. This was the moment. Both components were now locked in precise positions relative to the jig frame. Theory said they were now in correct alignment with each other. Reality was about to test the theory. Lower both cradles, Nowak said. Simultaneously. Kowalski and Turner each operated a chain hoist control. The lower cradle descended. The upper cradle descended. The gap between turret ring and hull ring closed. 12 feet, 10 feet, 8 feet. The crane cables creaked. The I-beam structure took the full weight without flexing. Nowak had calculated the loads correctly. 5 feet, 3 feet, 2 feet. Stop, Nowak called. Both cradles halted. The turret ring hovered 2 inches above the hull ring. This was the critical inspection point. Nowak walked around the assembly, looked at the gap from the north side, looked from the south, east, west. She could see visible misalignment on the west side. The turret ring wasn't parallel to the hull ring, about 0.03 inches of angular error. She returned to the control station, gripped the west adjustment wheel, turned it 3 clicks. Each click was 0.01 inches of movement. The upper cradle shifted east by 0.03 inches. She walked around again. The gap looked better, nearly parallel. Lower to 1 inch, she said. The cradles descended another inch. Now the gap was tight enough to measure with feeler gauges. Turner slid gauges into the gap at 4 points north, south, east, west. Called out the measurements: north 008, south 0, 0, 6, east 0, 0, 5, west 0, 0, 9. Translation: gaps ranging from 0.005 to 0.009 inches, all within acceptable range. Activate hydraulic rams, Nowak said. Even pressure, all 4 rams. Maximum pressure 2000 psi. Kowalski opened all 4 valves simultaneously. Hydraulic fluid flowed. The rams extended. The turret began descending into final position. Slowly, controlled. The rams applied 5,000 pounds of force from each cardinal direction, pulling the turret down evenly while preventing lateral movement. The pressure gauges climbed. 500 pounds per square inches. 1,000 pounds per square inches. 1,000, 500 pounds per square inches. At 1,800 pounds per square inches, there was a sharp metallic click, the sound of steel seating against steel. The turret ring settled fully onto the hull ring. Pressure stabilized at 1800 psi, Kowalski said. Rams holding position. Nowak walked around the assembly one more time, checked the turret to hull interface visually. No visible gaps. The mating surfaces were in full contact. She grabbed a feeler gauge, tried to slide it into the seam. Couldn't. The gap was too tight. Good. She tried a smaller gauge, 0.002 inches thick. It slid in about half an inch, then stopped. The gap was 0.002 inches or less around the entire circumference. Perfect. Release hydraulic pressure, Nowak said. Raise both cradles 6 inches. Let's test rotation. Kowalski closed the valves. Released pressure. The rams retracted. Both cradles lifted, taking the weight off the hull's support blocks. Turner grabbed the turret's gun barrel protruding from the front and pushed. The turret rotated, smoothly. No binding. No resistance. It spun freely on its ring bearing. He pushed it through a full 360-degree rotation. Checked for tight spots. Found none. Smooth through full rotation, Turner said. No binding detected. Nowak checked her watch. 6:37 a.m. She'd started lowering the hull into the cradle at 6 a.m. Total installation time, 37 minutes, compared to the previous average of 11.2 hours 672 minutes. This was a 94.5% reduction. The crowd had gone silent. Everyone had seen the same thing. A turret and hull that should have taken 14 hours to fit, that probably should have been rejected outright, had just been installed perfectly in 37 minutes. Morrison stepped forward, walked around the assembled tank, checked the turret rotation himself, tested it 3 times, looked at the installation seam, looked at Nowak. Run it again, he said. Different hull. Different turret. I want 6 installations today. If they all work, we're building 3 more jigs and putting them into production. Nowak nodded. Bring me the next hull. They ran 6 installations that day. Hull and turret pairs pulled randomly from the production queue. Average installation time, 31 minutes. Shortest, 26 minutes. Longest, 38 minutes. 0 rejections. 0 rework required. 6 perfect installations. By 6 p.m., Morrison had authorized construction of 3 additional jigs. By 8 p.m., he'd called a meeting with Army Ordnance to discuss implementing the design at other tank arsenals. By 10 p.m., Nowak was back in her apartment, eating cold soup directly from the can, too tired to cook. She'd just changed how America built tanks, and tomorrow morning she'd be back at 6 a.m. to do it again. February 21st. Morrison ordered construction of the second jig, assigned a full engineering team to document Nowak's design properly. They spent 3 days creating official technical drawings, clean, professional versions of her butcher paper sketches, added dimension tolerances, specified material grades, created assembly instructions, generated a bill of materials. The engineering team lead, a man named Howard Chen with a degree from MIT, reviewed Nowak's original calculations, found them flawless, every load path correct, every stress calculation accurate, every dimension justified. She did this in 3 nights? Chen asked Morrison. 3 nights, in a tool crib, with a pencil. Chen looked at Nowak's sketches again. I would have needed 3 weeks and a drafting team. Morrison promoted Nowak to lead tool designer on February 24th. Salary increased from $0.85 per hour to $1.10 per hour. She was now the highest paid woman in the arsenal, still made less than male engineers with equivalent responsibilities. But it was progress. The production impact was immediate and measurable. Week of February 22 to 28. Average production 11.2 tanks per day, up from 8.3 the previous week. The single jig in Bay 12 was handling roughly a third of all turret installations. The other 2/3 still used the old manual method. Week of March 1 to 7. Second jig operational. Average production 12.8 tanks per day. First time Detroit Tank Arsenal exceeded its daily target of 12 tanks. Week of March 8 to 14. Third jig operational. Average production 14.1 tanks per day. The turret rejection rate collapsed. February, 23%. March, 8%. April, 3%. By May, 1.2%. Average turret installation. Time dropped from 11.2 hours to 28 minutes. That freed up workers for other tasks. The arsenal reassigned 47 workers from turret installation to final assembly, addressing bottlenecks elsewhere in the production line. The bottleneck shifted. Turret installation was no longer the limiting factor. Now it was final drive installation, the mechanism that connected the engine to the tracks. Morrison assigned Nowak to that problem next. She spent 2 weeks observing final drive installations, identified the same pattern, parts within spec, process poorly designed, built another jig. Installation time dropped from 6.3 hours to 41 minutes. Then she tackled gun mount alignment, then engine to transmission mating, then track installation sequence. Each problem got the same treatment: observe, analyze, design, build, test, implement. By June 1943, she'd designed 11 jigs and fixtures for various assembly operations. 8 were in production use, the other 3 were still in testing. Colonel James Parker from Army Ordnance visited on March 10th. Watched the turret jig operate. Timed 3 consecutive installations with a stopwatch. Took detailed notes. Requested complete documentation drawings, procedures, material specifications, everything. We're building tanks at 5 other facilities, Parker said. They all have the same turret problem. How fast can you ship them blueprints? Already done, Morrison said. We sent the drawings to Army Ordnance last week. Good. I want this at every arsenal by May. Parker wrote a letter to Army Ordnance headquarters, recommending Nowak for the Army-Navy E Award, the highest honor for production excellence. The letter went through channels, made it as far as a review committee in Washington. The committee's response came back in April. Awards for production excellence are granted to facilities, not individuals. Detroit Tank Arsenal is hereby nominated for Army-Navy E Award based on production improvements. Nowak was never told about Parker's letter. Never knew he'd tried to get her recognized. The Arsenal received the award in June. The ceremony included speeches by Army generals and factory executives. Nowak wasn't invited. She was in Bay 12, training workers on the operation of the fourth jig. She didn't care. Recognition wasn't why she'd built the jig. She'd built it because turrets weren't fitting and tanks weren't shipping and men were going to combat without proper equipment. The jig fixed that. The numbers proved it. Everything else was noise. March 1943. Fisher Tank Arsenal in Grand Blanc, Michigan, received the blueprints for Nowak's jig. The facility was producing M4A, 2 variants Shermans with diesel engines instead of gasoline engines. Different power plant, same turret installation problem. Fisher's chief engineer, Robert Halloran, reviewed the drawings. His assessment: overcomplicated. We can simplify this design significantly. He eliminated the spring-loaded locating pins, replaced them with fixed positioning blocks, reduced the hydraulic rams from 4 to 2, cut the material cost from $14,200 to $9,800, built the modified jig in 3 weeks. First test on April 2nd. Catastrophic failure. The turret came down at an angle, bound against the hull ring, couldn't seat properly. They tried to force it with the 2 hydraulic rams. The uneven pressure cracked the hull ring, a stress fracture that made the entire hull unusable. One cracked hull, $18,000 in wasted material and labor. Halloran ordered the jig torn down, rebuilt it exactly to Nowak's specifications. All 24 spring-loaded pins, 4 hydraulic rams. Every dimension matched to the original drawings. Second test on April 14th. Perfect installation. 29 minutes start to finish. They ran 40 more tests, all successful. Average time, 27 minutes. Lesson learned. Every detail in Nowak's design mattered. The spring pins weren't decorative. The 4 rams weren't overkill. She'd engineered the jig for worst-case scenarios: maximum tolerance variation, marginal parts, misaligned components. Simplifying it meant it only worked with perfect parts, and perfect parts didn't exist. April 1943. Chrysler Tank Arsenal in Detroit received the blueprints, built 2 jigs simultaneously, both operational by April 15th. Production increased from 9.1 tanks per day to 14.2 tanks per day within 3 weeks. Chrysler's engineers made one improvement: added electric motors to the adjustment wheels. Instead of manual hand cranking for fine positioning, operators used push-button controls. Faster, more precise, less operator fatigue. Nowak visited Chrysler on April 28th to inspect their implementation. Saw the electric motors, approved the modification immediately. "That's better than my design," she said. "I'm adding it to Detroit's next jig." She spent 2 hours with Chrysler's engineering team discussing other potential improvements. They suggested adding position indicators with digital readouts instead of dial gauges. She agreed. They suggested adding automatic pressure regulation to the hydraulic system. She agreed. The jig was evolving, getting better. Different facilities were contributing improvements. That was exactly what should happen. May 1943. Pressed Steel Car Company in Pennsylvania began building M4A1 variants Shermans with cast hulls instead of welded hulls. Different hull geometry, different manufacturing process, same turret. Their engineers worried Nowak's jig wouldn't work with cast hulls. The datum surfaces were different. The reference points were in different locations. They modified the lower cradle, repositioned 6 of the 12 locating pins to match the cast hull's geometry, left everything else unchanged. First test. Worked perfectly. Principle proven. The jig concept, adapted to different tank variants. It wasn't specific to welded M4 hulls. It was a general solution to the problem of mating large components with variable tolerances. June 1943. Baldwin, Locomotive Works in Pennsylvania, building M4A2 diesel variants, used NOAC's design without modifications. Immediate success, July 1943. Pacific Car and Foundry in Washington State, westernmost tank production facility. Built the jig from blueprints alone, without ever seeing an operational unit. Worked perfectly on first test. That proved something important. The design was fully documented and completely replicable. Any facility with competent welders and machinists could build it. By August 1943, 11 tank production facilities were using NOAC jigs or variants. Combined production increase, 847 additional tanks delivered that month compared to January 1943 baseline. The tanks built using NOAC's jig went to war. Serial numbers traced back to production dates and facilities revealed which units received them. 3rd Armored Division, Normandy Invasion, June 6, 1944. The division's first wave included 47 Sherman tanks produced at Detroit Tank Arsenal between March and May, 1943. All 47 installed using NOAC's jig. After-action reports from July 1944 showed something unexpected. Tanks assembled with the jig had higher operational readiness rates. 89% remained combat-capable after 30 days of continuous operations. Tanks from earlier production runs assembled manually averaged 76% operational readiness. The reason? Better turret ring alignment meant less mechanical wear. The turret ring bearing was a critical component. It had to support the turret's weight while allowing smooth 360-degree rotation. Misalignment caused uneven wear patterns. Uneven wear led to binding, which led to bearing failure, which meant the turret couldn't traverse, which meant the tank couldn't fight effectively. Tanks with properly aligned turrets lasted longer between maintenance intervals. Their turret bearings lasted 40% longer on average. They required fewer replacement parts. They spent less time in field maintenance, more time in combat. Sherman serial number 5847. Produced March 18, 1943 at Detroit Tank Arsenal. Second tank through NOAC's jig after the initial testing phase. Assigned to 2nd Armored Division. Crew Commander, Staff Sergeant Robert Chen. No relation to Engineer Howard Chen. Chen's tank landed at Utah Beach on June 6, 1944. Fought through France. Participated in the liberation of Paris. Pushed into Belgium. Crossed into Germany in March 1945. 11 months of combat operations. The tank took 3 hits from German anti-tank weapons. Survived all 3. Required engine replacement once. Required track replacement twice. Never required turret bearing replacement, the most common maintenance issue for Shermans in extended combat. Chen's maintenance log, preserved at the National Archives, includes a note from September 1944. Turret traverse remains smooth. No binding detected. Best tank I've served in. Chen's crew survived the war. All 5 men. They attributed their survival partly to luck, partly to tactics, partly to having a tank that worked reliably when they needed it. Chen never knew about Margaret NOAC. Never knew his tank's turret had been installed in 26 minutes using a jig designed by a factory worker from Hamtramck. He just knew his tank was reliable. The indirect impact was harder to measure but equally significant. Faster production meant more tanks available. More tanks meant more tactical options for commanders. General Omar Bradley, in a 1952 interview, discussed the importance of tank availability. We could afford to be aggressive in 1944 because we knew replacement tanks would arrive quickly. We could take calculated risks. We could commit armor to operations that might result in losses, knowing those losses would be replaced within days, not months. 847 additional tanks in August 1943 represented 17 full tank battalions worth of equipment. Those battalions deployed to Italy in fall 1943, later redeployed to Britain for the Normandy invasion. Military historians analyzing the European theatre have noted that increased tank production in 1943 directly enabled the multi-front strategy of 1944. Simultaneous operations in Italy and France required massive armor reserves. Those reserves existed partly because factories like Detroit Tank Arsenal were finally hitting their production targets. Nowak's jig didn't win the war, but it helped deliver the equipment that did. October 1943. Society of Automotive Engineers Annual Conference, Detroit. A paper was presented, Advanced Fixturing Methods for High-Volume Armored Vehicle Assembly. Authors, Richard Morrison, Plant Manager, Detroit Tank Arsenal, and Margaret Nowak, Lead Tool Designer. First time Nowak's name appeared in official engineering documentation. First time she was listed as co-author on a technical paper. First time her work was presented to the broader engineering community. The paper described the jig design in detail, explained the spring-loaded locating pin concept, presented data on installation times, rejection rates, and production increases. Included photographs of the jig in operation. Conclusion. Spring-loaded locating pins and multi-axis hydraulic force application represent significant advancement in precision assembly of large components with variable tolerances. The principles demonstrated in turret installation are applicable to other high-volume manufacturing operations requiring precise alignment of heavy components. The paper was received politely. Some engineers asked technical questions. Most were skeptical that such simple principles could yield such dramatic results. One engineer from Ford Motor Company asked if the data had been manipulated to make the jig look more effective than it was. Morrison's response: "Come to Detroit Tank Arsenal, watch it operate, time it yourself. The data is conservative, if anything." 3 engineers accepted the invitation, visited the arsenal in November, watched 6 turret installations, timed them, measured the results, went back to their facilities convinced. The principles spread beyond tanks. November 1943. Boeing aircraft adopted a similar concept for B-29 Superfortress fuselage section mating. The B-29 was built in sections forward fuselage, center fuselage, aft fuselage, manufactured at different facilities and assembled at final assembly plants. Alignment problems were common. Sections that didn't mate properly required hours of manual fitting. Boeing engineers read the SAE paper, adapted Nowak's locating pin concept, built a jig for fuselage assembly. Results: assembly time reduced from 18 hours to 6 hours per aircraft. Rejection rate dropped from 12% to 2%. December 1943. Bath Iron Works in Maine, building Fletcher-class destroyers. Applied the principle to turret installation on naval vessels. 5-inch gun turrets weighing 14 tons each. Similar alignment problems to tank turrets. Similar solution. Similar results. January 1944. Consolidated aircraft in San Diego, building B-24 Liberator bombers. Used adapted jig design for wing attachment. Wings manufactured separately from fuselage. Critical alignment required for proper flight characteristics. Nowak's locating pin principle solved the problem. The concept was spreading across different industries, different applications, different scales. The fundamental principle remained the same: constrain components in known positions, compensate for variation automatically, apply controlled mating force. Post-war recognition came slowly. American Society of Mechanical Engineers published a case study. Wartime Manufacturing Innovations, the Nowak Turret Installation Fixture. Detailed analysis of the jig's design and impact. Estimated total labor hours saved across all implementations, 1.8 million hours. Equivalent cost savings, $4.3 million. The case study became required reading in manufacturing engineering programs at 3 universities. Students learned the principles. Most didn't learn who Nowak was. The case study referred to her as the designer or the tool builder. Only in footnotes was her full name mentioned. General Motors hired Nowak as senior manufacturing engineer, first woman to hold that position in GM's history. Salary: $4,200 per year. Male engineers in equivalent positions, $5,800 per year. She didn't complain. It was still 3 times what she'd made at the arsenal. She worked on post-war automobile production tooling, designed fixtures for engine assembly, transmission installation, body panel alignment, applied the same principles she'd used on tanks. Several of her jig designs remained in use through the 1,960 seconds. Korean War, 1,950 to 1,953. M46 Patton tank production used an evolved version of Nowak's jig. Larger tank, heavier turret, same principles. Installation time, 32 minutes average. Vietnam War, 1965 to 1973. M48 and M60 tank production facilities all used locating pin and hydraulic ram systems derived from Nowak's original design. Installation time, 19 minutes average with semi-automated controls. 1,970 seconds. Chrysler Defense, building M1 Abrams tank. Engineering documentation credited Nowak's 1943 design as the foundation for their automated turret installation system. Modern version used computer controls, laser alignment, and servo-driven positioning. But the core principle spring-loaded locating pins finding datum surfaces remained unchanged. Margaret Nowak worked at Detroit Tank Arsenal until May 1945. Germany surrendered on May 8. Japan surrendered August 15. Tank production ceased. The arsenal began shutting down production lines. Between February 1943 and May 1945, Nowak designed 23 additional jigs and fixtures for various assembly operations. 11 were adopted for production use. 5 were still in testing when the war ended. 7 were rejected not because they didn't work, but because the problems they solved were resolved through other means. Estimated total labor hours saved by her designs: 1.2 million hours. Equivalent cost savings at 1,943 labor rates, $2.88 million. Return on investment, approximately 800%. She never received military decoration, never received presidential citation, never invited to the White House. Her name appeared in exactly 3 official Army documents during the war: Colonel Parker's award nomination that was rejected, the SAE technical paper, and the patent filing, June 1945. Nowak left the arsenal, hired by General Motors, Flint Engine Plant, senior manufacturing engineer. The hiring manager, a man named Thomas Whitfield, had read the SAE paper. He knew what she'd accomplished. "We need someone who can solve problems the way you solved the turret problem," Whitfield told her during the interview. "We have bottlenecks in engine assembly, parts that don't fit properly, processes that take too long. I need someone who sees solutions instead of obstacles." She worked at GM for 17 years, 1945 to 1962, designed tooling for post-war Chevrolet and Buick production. Engines, transmissions, body panels, suspension components. Filed 14 patent applications, received 11 patents, all related to assembly fixtures, alignment tools, and positioning systems.